right, so it's 1 o'clock. We'll jump straight in. My name is Bryan Kelly, and I'm a Principal Firmware Engineering Manager at Microsoft. And welcome to OCP Summit 2018. So today, I'm going to talk about Project Cerberus, and we're going to start. This talk is going to include the cloud, a little bit about the cloud security threat model. We're not going to dwell on it. State of the industry today, which kind of gives us a little bit of a background for the reasoning for Project Cerberus. And then we'll do a quick overview of Project Cerberus, and then what we call a Project Cerberus Deconstruct. We'll go into some more detail about it, and then a little bit about the activity that's happening in the Open Compute Security Project. So jumping right in, where are the threats in the industry today for the cloud? We've got the traditional attack, I guess, or conventional attack vector, where we have attackers, network access, trying to do network penetration, all that good stuff. We've got compromised cloud customers, so customers that may have some malware are on their system. That's trying to spread to online services. We've got malicious enterprises and malicious enterprise employees. Malicious cloud contractors, malicious cloud employees. Attacks in transit. So before the components or servers or systems actually land in a secure cloud data center, there's possible attacks during the path there. System integrators, which take all these components, put them together, and maybe ship a single component, such as a server that comprises of a motherboard, CPUs, memory, disks. Putting all those components together usually happens at an integration facility. That too is a potential attack. And then at the very source, at the supplier itself, which is a component manufacturer. Firmware attack surface. What does the surface of a firmware attack look like? We've got driver and firmware attack itself. If you have network access, network is a potential penetration point. You've got boot, attacks at boot up, pre-boot and post-boot. Inside at an OS or a hypervisor level, if there's direct access given to the hardware for performance, that's also a potential attack vector. And then there's when these, we're talking here today about really Project Cerberus and firmware security. So with firmware, the detection once you've been compromised is relatively complex. And traditionally, the challenges of getting that recovered or brought forward to a good state is also another challenge. And then, of course, the impact can be loss of data, denial of service, or even loss of an asset. So there are some guidelines out there in the industry. Last September, there was a draft of the platform firmware resilience guidelines published by NIST that essentially has 3 guiding pillars inside in it when we review and participate in that. There's protection, detection, and recovery from firmware attacks. And most of what we did when we were designing Cerberus is we had a similar philosophy of how do we protect and stop us getting into a stage where integrity is brought into question, and then how do we detect if integrity is compromised, and then how do we bring our state forward and recover from that compromised state. So back when we started Project Cerberus, we did a look at the state of the industry and where the traditional server security lay. We took a look at what components are typically found inside a modern enterprise server, and then the level of security at which we felt that have to review the level of security at which these components had. And that brought us to UEFI. So varies from platform to platform, from silicon manufacturer to silicon manufacturer. There's varying levels of protection on UEFI. There's some forms of secure boot. There's no protection. When we go back to this NIST standard, there was no protect, detect, or there was no recovery and protection from getting into a compromised state. And then when you're in a compromised state, how do you get out of it? Of course, secure boot will verify that the integrity of the firmware, but it's kind of an act too late if you've already been compromised, especially at scale. We then extended that out. We looked at BMCs. The security story there wasn't that good. And then we also dug into the various peripherals, and the situation didn't really get much better. This is a generalization of the state of the industry. I know some of you might say, hey, we've got components that have this or that. And, at large, this is the state of where enterprise security is at today. So that brought us to Project Cerberus and the introduction of Project Cerberus. And I thought I'd start it off talking about what Cerberus is, with maybe some of its properties. So it is a hardware-based root of trust. What that entails is it has an unforgeable identity that's unique. It's cryptographic keys, and it's all protected by the hardware. It's a small TCB. It's pretty much a single function device. Its purpose is security. Its purpose is not to send packets over the network or to store data out on some flash. Its purpose is security. And with that, it's pretty small when it's a single function device. It has a lot of security intrinsic to it, such as compartmentalization. Another attribute of it is it has certificate-based authentication. It's got attestable integrity, and we're going to jump in and dig into some of these properties a little bit later on. It's got renewable security, in that if there is security compromised, the security state can be brought forward to a secure state again. And then it's, of course, modular security. So as you've seen probably from the keynote and from documents online, it does interpose on, it doesn't only attest to its own security, but it interposes essentially between a CPU and its firmware load store. And if that CPU or that component doesn't have the level of security that we require, it gets interposed and provides that level of security. So a little bit more about what Cerberus is. Your typical system. This is a real rudimentary block diagram of BMC and the CPU going out to some SPI flash. We've also got a NIC with some flash as well. Where Cerberus sits is in between the CPU and its flash, and it enforces secure boot. And we're going to get in a little bit later on into some more details around what secure boot is in a Cerberus world. But it enforces those NIST 193 standards of our principles of the protect, detect, and recover. Cerberus is hardware agnostic. It goes motherboards and headless chassis that maybe we don't have a CPU, goes into expansion chassis and so on. This is just, it also performs attestation between the various components, the various Cerberus components inside in the motherboard. It has what we call a platform attestation, and our platform attestation goes back to a single Cerberus that we put on the baseboard, whether it's a chassis or it's a compute chassis with host CPUs, or whether it's some storage or acceleration chassis. We will have a root of trust on that main board, and that will it won't enforce secure boot on the subcomponents in it. They'll have their own secure boot. They'll have their own attestation, but those measurements will get rolled back to that platform Cerberus or root of trust. Now, that's not to say that the authentication between them is hierarchical or anything like that. There is authentication between these components, and we'll get to it in a little bit, but it is not hierarchical. So the protection, how does Cerberus provide protection when it sits in between the flash and the CPUs? Of course, it enforces what we call region protection. So it understands the firmware layout through what we call platform firmware manifests. And they describe basically the read-only and the read-write regions of firmware. And then Cerberus policies, filters, spy traffic, and only allows writes through to regions that we deem should be written to in flash. And it only allows reads through to regions we deem should be read from flash. So the detection, we're gonna get into this a little bit more later on, but the detection that Cerberus does is it has secure boot for its own firmware. And when I say secure boot, I'm talking about digital signatures match the keys that we have fused in hardware. So we're going to jump into this a little bit later on in some more detail, but this is a high-level overview of how Cerberus security works. It works both pre-boot and post-boot. It can perform these firmware integrity checks, and it can attest to the firmware as well. And then the other principle that was in those that NIST guideline for firmware resilience was recovery. And we have policy-based recovery, where we'll have regions of the flash are made read-write. We'll have a backup version of the firmware that is like a golden copy, that if we should get compromised in any one area of flash, we can recover it from our backup copy, and that can happen automatically. And then I mentioned this a little bit earlier, is the hierarchy for Cerberus. It is a hierarchical design. We do have that master root of trust that we put on the motherboard. Peripherals will then either have the same capabilities intrinsically, or they'll have the Cerberus ASIC interposed between their processor and their firmware load store. And that will enforce the NIST 193 principles at each level where the platform firmware is. And then the master, of course, when we get into our attestation gets rolled up from all of these components back to the master. So the master keeps a measurement that's continually extended for the platform. So not only does each component have its own measurement, but it takes its own measurements and it rolls those back to the master through a challenge protocol. And the master attests to the platform measurement. So there's a single platform measurement and a log that's very similar, if you're aware of it or not, the TCG log that comes with TPM measurements, so you can replay as to how that measurement was calculated. So the Cerberus ASIC, what is the Cerberus ASIC? We talked a little bit about this earlier when I talked about the properties of Cerberus, but it is a dedicated microprocessor. that we call our root of trust. It's got some crypto acceleration blocks. It's got some fuses in there for our boot keys. It's got a puff, a hardware puff, which we use as a source of entropy combined with some other information. We also derive some keys for that, for device unique encryption and that kind of thing. It's also inside in the ROM. It has the device identifier composition engine, which is part of TCG, and this is really the foundation of how we achieve our attestation of Cerberus itself. And then, of course, the real special interface that's on Cerberus is the SPI. We call it SPI, QSPI. It does all flavors of SPI, but the SPI bitstream filter is what protects the flash. So as flash transactions are coming in, Cerberus can filter those and determine whether they should be allowed, get committed to flash, or whether they should go elsewhere. So getting into some details on Cerberus, we'll jump into the Cerberus kind of a deconstruct. We'll go through some unique characteristics of it. We have our power sequence, our Cerberus boot itself, Cerberus attestation itself, then a platform boot, and then how it does platform attestation, and then a little bit about provisioning, how we provision Cerberus, and then some more about revocation. That's not on the list here, but I know it's in the deck if we get to it. So the power on sequence for Cerberus is kind of a contentious point for many people in the security forum that have reviewed Cerberus. But as a root of trust, we power it on first. It has to establish trust. To be booted up and fully running and then try to establish trust is very complex. So a power on, the first component in our motherboards that powers on is Cerberus. It then holds other components in reset, so essentially in an off state. It holds the CPU, the BMC, and inherently, CPU is off, CPU complex is off, inherently PCIe is also off. If those components come out of reset, they're not going to do anything. They're just going to probably have an error because they're not going to be attached to any SPI flash at that time. They have to go through Cerberus, so it has to take them out of reset in order for them to, it has to first give them access to flash before it takes them out of reset. So Cerberus will power on, and it will do its own secure boot, its own measurements, and send out its own attestation. Then, when it's done with booting itself, it goes and reads the BMC flash. Cerberus internally has what we call a platform firmware manifest that we'll get to. And that manifest essentially tells it what BMC firmware it should expect on flash and how to take a measurement of that BMC firmware. Cerberus will go and take those measurements. It will compare the digest of the BMC firmware with the digest that it internally stores that's been signed as part of the firmware manifest that sits in Cerberus. When it's got the BMC securely booted and loaded, or it's finished that process and released it from reset, it will also be doing the same for the CPU. It's number 4 here in the diagram, but it's not in, 4 is not the, this is the boot, this is the power on stage essentially for us. It's not the order on which Cerberus is going and interrogating flash. So after it's authenticated the UEFI flash, it will simultaneously be looking for measurements to come back from the PCIe devices. If that all attests good, it'll bring the system out of reset. If it doesn't attest good, it's got some options. It may still bring it out of reset, or we may decide to send it out for repair to understand why it's not attesting correctly. That's the power on sequence of the motherboard. It's a little bit of a change where everything comes on at once. So Cerberus boot and how Cerberus boot works. So there's a public key that we have a hash of that gets stored in hardware eFuses, and that digest at a public key in eFuses is compared against a public key that's on mutable storage inside in Cerberus. And if the digest of that key, so the part I'm kind of talking about, if we get a laser pointer, we go over to the diagram here. Let me see. If this key, when Cerberus powers on, it'll go out, read this key from mutable storage, and it will hash it. If it doesn't match, then it will fail over to the next boot device that it has in its boot order. If that key does match what's in hardware fuses, it will then go and, there's a step I kind of glossed over. It's kind of, it's a step that in the whole security chain here doesn't really add much value other than obfuscation. So what we do, encrypt the key on flash. And on boot, it decrypts that. The security value of that in secure boot, whether it's encrypted or not encrypted, it doesn't really add any advantage there, other than what I said is obfuscating what's on flash. But it will decrypt that key and then compare it to what's in OTP. Then it will also go and decrypt the first part of mutable firmware that we have that we call a key manifest. And this is really just a table of key hashes that we keep on flash. And these key hashes are used in other parts of the boot process. And they're also used a little bit later on for some firmware functions in the application firmware. But the ROM will take a digest of the key manifest, and it will compare that using the public key to the digital signature that is also stored on the mutable storage inside in Flash. Once the ROM has authenticated the key manifest, essentially by comparing its by verifying its public key, its digital signature, it will then take a key from the key manifest and do essentially the same process. Using that key, it will verify the signature of the next stage in our boot firmware, which is a little piece of firmware we call Riot Core, and there's some specifications online about that. We'll get into Riot Core a little bit later on, what exactly it does, but it does the same. The ROM does the same verification against the key manifest and against Riot Core, and then it will launch Riot Core and pass it in a composite device identifier, which is a ROM secret that gets hashed with the measurement of the key manifest and Riot Core. And from that, we're going to get into what what the CDI is used for in a little bit. It's used for generating keys. So that unique composite device identifier, which identifies our firmware, it uniquely ties our firmware to that specific instance of Cerberus, or that specific component. So it's not our firmware running on a different device, or our firmware taken and putting on some other device. The CDI would change. So the CDI is essentially the measurement of the key manifest and riot core hashed with a secret that's only accessible to ROM, a unique device secret that's only accessible to ROM. And that unique device secret is derived from some security state, some numbers that we keep inside in the ROM that identify that part, and the puff. So that's where the hardware puff comes in as the source of entropy across that as well. Then when riot core boots, it will take another key out of that key manifest, and it will authenticate the application layer or the Cerberus firmware layer. And the Cerberus firmware layer will then go and start to perform a similar boot flow against BMC, against BIOS, and it also has some I2C communication to other devices in the system where it will start to gather their measurements and compile that into a platform measurement. So the riot core block that we just discussed, so the ROM will calculate the CDI down here, and it will use the measurement of riot core and the CDI. Riot core and a firmware manifest. It's kind of the ROM treats it as two kind of blocks, but firmware-wise, we treat it as a single block. So that measurement combined with the device unique secret or HMAC with the device unique secret gives us the CDI. And then the CDI is used to derive keys. And these keys that are derived from the CDI, if our riot core block changes or our firmware manifest changes, the CDI changes, and then any of the certificates, any of the keys, and ultimately the certificates that get generated from the CDI, they also change. So when riot core loads, it generates asymmetric device ID key here, and it will also generate an alias key. The alias key is different to the device ID key. The device ID key is used if we want to talk specifically to the riot core level of firmware. The alias key is used by the Cerberus application firmware if we want to go and talk with that application firmware. Of course, our device ID key during manufacturing is CA signed, so we send out a certificate signing request, and then we will sign that certificate and send it back to the device. And then on the next boot, when the device derives those keys, it will check, and it will already have a signature that matches that key, so it won't continually send out that CSR. The boot continued into maybe some of the attestation levels of Cerberus. So after the riot core, I'll step back a sec. After the riot core generates these certificates, we then have a way to talk with riot core and with the Cerberus application firmware as well, and we send them different things. So for example, for freshness measurements of the Cerberus application firmware, we would encrypt that with the public key using our device ID certificate, and we would send that back to Cerberus. And then the only part in our firmware load sequence that can decrypt that freshness seed is going to be riot core, as the private key for the device ID is only accessible to the riot core level of boot. So whereas the alias key, we send the private key and a public key up to the application firmware. So we have our, when I went back to the properties of Cerberus and I talked about certificate authentication, we have certificate authentication at different levels of the Cerberus firmware itself. This is still within the microcontroller. We haven't gone out and started to talk with the measure BMC firmware and so on. This is just within this small microcontroller. So then if we want to send different attestation freshness seeds to the various areas of Cerberus, we can do so using these unique certificates. The certificates themselves are derived from a ROM secret and the measurement of the firmware. So if anything changes, the certificates become essentially invalid. So the attestation seed that I kind of talked about for freshness and how we get that down to Cerberus, if we want to attest to the Cerberus firmware itself, to the application firmware, we would send that seed down to Riot Core, where it has access to the private key to decrypt that seed and then to include it in the new measurement of the Cerberus application firmware and seal that measurement and have it sent back, sign that measurement essentially, and have it sent back to us. In addition to some of the measurements that we send back here, I kind of mentioned it earlier, but glossed over it. We also use the TCG style log for measurement measurement replay. I guess you would call it. So we can determine if a component inside in there fails to attest, which component it was that didn't attest, or which measurement caused the ultimate platform measurement not to attest. So at the application layer of Cerberus, we can also send it attestation seeds or have it extend the measurement that it got passed from the Riot Core level to go out and attest BMC firmware. So when it measures what's out on flash for the BMC, it can include that in the platform measurement. We can also add freshness seeds in there to prevent replay and so on. So how the application firmware in Cerberus really works is it works off of a thing we call a platform firmware manifest. And the platform firmware manifest informs Cerberus of a couple of things, of the devices that it's securing, the devices around it that it's securing. Cerberus is interposed between a CPU and some flash. It has to understand a little bit about what it should be attesting out in the flash. So we provide to it, now we don't provide it in XML structure, but when we're building it, we build it in XML structure, and then we have a tool that converts it into a readable structure from Cerberus, and then we also have that manifest gets signed. Now, there can be multiple versions inside in a manifest. So if we take a BMC, for example, we could have a firmware manifest for the BMC that includes 10 different BMC versions, and that will get sent to Cerberus, and then it will review those versions when it gets sent. It will verify that the manifest has been signed with the right key, and then it will also check if it's currently supporting a version in that manifest. If it's not currently supporting a version in that manifest, it will reject it. So the version inside the manifest has to at least include the current running version of firmware that's out on the BMC. So manifest includes some version information about the firmware version, the firmware versions that it's supporting. For each firmware version, it will include the read-only flash descriptors. So the areas in flash that are read-only, they contain code, and they're going to be part of the makeup of the digest for the digital signature that is inside the manifest. So it'll also have the write regions, and if a region is undefined, then it's not accessible. So it's no reads or writes are allowed to undefined regions. So the digest of the code blocks and a public certificate for authenticating the signature that we have on those that makes up that digest. So we sign it still. So then Cerberus will use this information when it's going out and verifying the integrity of flash. It will create a digest essentially using the read-only regions of flash. So we'll go out, measure what's on flash, and ensure that measurement matches the PFM, what we have signed inside the PFM. And the reason you might ask, why doesn't it just do a hash, just verify the hash or whatever of the BMC? Why does it have to have a digital signature associated with it? And that's really for some internal controls and people submitting. Multiple firmware teams we have that may be submitting firmware versions. Part of a process for security review and code review is after we have reviewed the code and leads have signed off on that particular piece of code, it will then go through a security audit, and then we'll get to a stage where it's submitted for signing, and then when it's signed, it comes back and it's that digest that we use. So you can't arbitrarily say, hey, I got a new PFM that I want to go create. It still has to follow our same process for all digitally signed firmware that we use. So it uses the digital signature in here too. And it's also helpful when we get into some revocation. We have like soft revocation and hard revocation of firmware that may have a vulnerability in it, and we never want to, roll back. We always want to roll forward, that kind of thing. So the PFM ultimately describes to Cerberus what it is it's supporting and how it should appear. So I talked a little bit. Sure. I'm rattling off here. I probably should have stopped a little bit earlier, but this is a work group. So feel free.
So the thing is, when somebody updates the BMC firmware or BIOS firmware,
yes.
So they will first
send a PFM.
Manifest, update the manifest first, and then go update, or.
Yeah, so it's first update the manifest. So actually, in our utilities that we go when we flash, like flashing BMC or flashing BIOS, we added a utility or step in front of that. Now it's kind of blind to the end user, but we send a manifest to Cerberus, and we've kind of abstracted it that they don't even see it. So I give you a BIOS update. The first portion of the BIOS update is, that first portion of that binary file that I give you, that's actually a manifest that I first, when I'm updating the BIOS, I strip it off, I send it to Cerberus, and then I send the update. And in fact, I can send manifests ahead of sending updates. Those processes, they don't have to be sequenced in any particular order. So if you send a manifest, if you send a firmware update that's not in an existing manifest on Cerberus, that firmware update is not going to go through. So it prevents unsigned firmware from going down to the device. How it knows, how it authenticates the firmware signatures is, again, using the manifest. So if it's not in a manifest for Cerberus, it's not getting to the flash.
Why do you choose sort of a whitelist approach instead of a blacklist approach?
Because it gives us, it gives us more control of what's running in our fleet. We like to keep everything refreshed and up to date, as opposed to a blacklist. But you can take either approach. I think it's just philosophically we want to approve what's running, not approve what shouldn't run. So it's philosophical, I think. But either approach could work. All right. Yeah, so we'll walk through how it would go and authenticate the BMC, and essentially to Cerberus, this is kind of what it looks like. It's got a clump of regions that it has as read only. Then we've got a read write FS, and then way out here we've got some metadata that we like to keep about the firmware that's on the flash. So the PFM describes the firmware digest structure. So that's going to say from region 000 all the way up to E9 FFFFF is what's actually signed, and then it would include this other read-write offset. So then what we would go and get digitally signed offline would be the read-only regions here. And then Cerberus would go out and read those regions and recalculate that digest. And then, in addition, it is active all the time on the SPI bus with that SPI filter logic. So it's enforcing read-only regions and read-write regions. So if I try to write to a region that's read-only, it will block it. If I try to read from a region that has not been defined as read or write, it will block it. And this is where, often on flash, what you have is you buy a 32 meg or 64 meg flash and you only use 16 meg of it. Secure boot and stuff and other technologies, they'll help verify that 16 meg, but you got a bunch of malware sitting beyond 16 meg that you're just blind to until there's an exploit in firmware that jumps to that region. And often flash is memory mapped. So we enforce strictly read regions as well as we do write regions. And if a region is not defined as read-only, you can't read from it. You could just get back FFF, right? As I mentioned earlier, a little bit, the measurements that we take are then extended, so hashed with the measurement, again, of Cerberus itself, with that freshness seed that's been put in at the start. Our filter supports runtime protections. The technology here too, it still works with flattened image tree, so fit tables. So for the BMC specifically, if it intrinsically has a secure boot, or if you lay it out in a way where you have fit tables, and for those that don't know what a fit table is like in U-boot and how you describe the kernel, you can actually have those images described with a table that has kind of a thing like a platform firmware manifest, essentially. So it will still work. It can work too with fit tables that have been derived or inserted into the firmware. If the firmware is laid out in a fit format, it can also work with fit tables. And then UEFI and the other components are essentially measured in the same way. So they will have their own PFM. So when we have Cerberus that is on a motherboard that is protecting the BMC and the UEFI, and it's enforcing secure boot and attestation, it will actually have different PFM. It'll manage a different PFM for each of them, so they can be updated at different rates and have their own platform firmware manifest. So I've only got a few minutes, so I might quickly gloss over the next section. But A kind of a unique thing we added to Cerberus on the on a motherboard is we kept a golden copy or recovery of our U-boot environment, and we actually stored it inside in Cerberus. And this is kind of unique to just the BMC configuration. So how we talk to Cerberus is actually we talk to it. Maybe I should jump to that slide first. So how we can talk to Cerberus is we have a couple of interfaces on how we talk to Cerberus. And we can talk through it through our SPI interface, of course, because it's connected to the host CPUs. We can talk to it primarily through our BMC, actually. So where it says SPI down here should actually say I2C. It's a typo. But the BMC has an I2C channel that goes to Cerberus, and that I2C channel can be queried from the host. When I talk down from the host via KCS or LPC or I2C, depending on the hardware architecture, the hosted BMC can proxy messages from the host through to Cerberus. Now, it's still authenticated. Everything that Cerberus will accept has to actually be authenticated, and this authentication works over those keys that I talked about earlier when we were talking about Riot Core. So from the host, you can our attestation, Fabric attestation service will go in and talk to the host, which in turn would have talked down to Cerberus. We also go out of band. And by out of band, we mean through the Olympus rack manager architecture down to the BMC. The BMC itself has Ethernet on it. Cerberus does not. And then from out of band, you can talk through the BMC to Cerberus. So your communication with Cerberus is through the BMC. There is another SPI path, but it requires the host to be up and running, so we can't always rely on that one. So the communication to Cerberus is through the BMC. So if we had BMC firmware that was compromised somehow, and then the backup copy was also compromised somehow, we would have this internal recovery, Cerberus bringing its communication path up, which is essentially a small U-boot image that it would then push out onto the BMC flash and have the BMC boot from Cerberus's golden BMC image, which in turn NFS mounts a golden image for the BMC that we store in the rack manager. And that gives us back our Cerberus communication path. It's kind of a little hook that we built in, but not part of the overall architecture.
Does your BMC have a dedicated NIC?
It does have a dedicated NIC, yeah. Yep. And that goes to another device that's in our rack. So we don't operate at the. I'm often asked, what is a component? Is a component a NIC? Is a component a server? And the component means different things to different people. So the component for us is the rack. That component gets deployed. Yeah.
Bryan, why didn't you guys just consider putting the NIC on the servers, like a simple, slower management NIC?
Onto Cerberus itself?
Yeah.
So we had thought about that, and then it kind of becomes a limiting factor. We want to keep that small TCB. So we didn't want to open that up and add that into Cerberus and make Cerberus a little bit bigger itself and have another attack vector. I was talking to somebody a few days ago that they had a technology, and they were talking about that technology as a TCB, and then it was essentially a TPM that had a NIC on it, and then there was all sorts of firewalling and complexities that the introduction of that NIC brought. So on this path, we actually just take it through the BMC. And as well as that, it cuts down on additional cable coming through. We don't ever envisage our root of trust becoming a management processor or doing more functions. And this is often the problem with security technologies, is if you make it too generally useful, it gets overloaded. And everybody says trust zone, right, when you say that. But it's true. If a security technology is too generally useful, you start to gradually, it's really difficult just to keep it as security. So we wanted a small, dedicated TCP. And then Cerberus as well is designed, it's small, very small ASIC. It's designed to interpose between the CPU and the flash. So when you get to forcing it onto components and stuff, having a NIC there just didn't make sense.
How is the impact of all this process in the OCPUS times, the BMC boot times? Do you have any measure how much this will cost?
Yeah, of the boot stack. So when the system is off, is when we're doing a lot of that key, deriving the keys and certificates and so on. So that part happens in the Cerberus itself. So that's only really in our cold boot path to get the Cerberus. And then the warm reset path, we actually have somewhat optimized inside in there. But we still take measurements in our warm reset path. But our reset is very, very much optimized and different to everybody else's reset. So yeah, we got a very special reset. So.
Is Cerberus intended to be a discrete SoC, or would it be possible to package it with some other system component?
Yeah, great question. The end goal is to have the functionality. I think I like it intrinsic. Security is always better if it's intrinsic inside in components. There's a lot of vulnerabilities on bolting a thing on the side. There's a lot of trouble in bolting the thing on the side. The challenge is it's not. It's not intrinsic in components. It's not intrinsic in components that I can buy today. It's not intrinsic in components that I can buy tomorrow. It's not intrinsic in components that I can buy 2 years from now. So that's the real challenge, is when do we have the level of intrinsic security in all components and they can all come back in a test? When do we have that? And that's something that we're working through with the security project in OCP right now. And we were talking about it just before lunch and before this meeting. One of the frustrations is the pace even in getting these security agreements and specifications and everything ready is slower than we'd like. But end goal is to get to a secure state, and we're not at a secure state. So we do build silicon in-house. So some components we build in-house, and when we do that, we intrinsically put in Cerberus functionality. It's just a wise thing to do. Then we're not going to, hey, look, we built this, great offload, but now we got to bolt on security. No, we'll make sure that we design it in from the beginning. Shoot.
As a plug-in device, it can't be compromised then if the enemy pulls that device out and tries to bypass its capability. Does it render it useless and you can't function without it?
So physically, if you have physical attack, you can do a lot of stuff. Yeah. So physical attack is a tough one to battle, especially at a server. Consumer device where it's kind of locked down, and you can add like all sorts of tamper detection and meshes and stuff like that. On a server where it's designed to be flexible with lots of stuff plug into it, same motherboard, really tough to address physical tampering. And how we tend to do that is up level it to the chassis. And even still at that point, it's tough. And then it gets up level to the rack, and then it gets up level to the colo, or the cage within the colo, and then the colo, and then the data center, and that's how the physical security is typically addressed. But you're right, physical security is not something, a separate security processor that you bolt on will address. But the physical security anyway takes a lot more. Even with intrinsic security, there's a lot of challenges with physical tampering. So. Shoot, Adrian.
Yeah, physical security maybe you're a little bit out of step. How about things in terms of servers? How do you view things with regards to side channel analysis? So things like timing attacks. So you have a pretty complicated Bryan flow, generation flows. That has a lot of implications as to what the firmware can do with all this time.
Yeah. So again, like physical attacks, like trying to get in on top of a reset and trying to get into a memory, on a memory vector or something like that. That one is again a physical attack. That's just okay.
Timing is different. You're looking at how long something takes to boot, for instance, or how long it takes to do a key derivation of an RSA private key, for instance.
Yes.
You can see things happening.
Yes.
And it's software visible, right? So that's the question.
Yeah, so it's not software visible when we're doing our key derivation. There's no interfaces into the device other than a special I2C interface that you have to send it a signed message before it's going to respond. So,
Do that kind of thing with power analysis?
yeah, well, that's physical attack, and that's tough, right?
Do you have blinding of any sort to prevent those kinds of
Yeah, it's super tough in a server environment to add that level of physical security and still be flexible. So yeah. I did want to mention one thing is kind of revocation. Another aspect of the PFM is firmware revocation. So that gets down to the whitelist, blacklist. All of a sudden it gets, we take a version off the whitelist. You can never go back and put that on. As well as that, the PFMs, we made the PFMs forward only. You can never roll back a PFM. Even a signed PFM, Cerberus firmware, if he's got a newer PFM, he won't accept a lower PFM version than the one it has. And then we do have hard revocation on our key manifest. And a hard revocation is done using a manifest ID where we can blow some OTP memory bits to revoke manifests that we have. And that, again, is forward only.
Bryan,
Okay.
you're saying that the PFM version is tied to the anti-rollback version? It's one and the same?
PFM is separate from the key manifest. Key manifest is the key manifest. This part is done by that's what our ROM is authenticating, and that is blowing OTP bits. The platform firmware manifest, everything we call manifest, so it gets kind of confusing. But the platform firmware manifest tells you what versions of BMC, what versions of BIOS are allowed to run on the platform. And that is a forward-only thing because it's enforced by the Cerberus application firmware or the Cerberus firmware.
Okay.
And
there are use cases where you might want to go to older firmware.
Yep, it's roll forward for us.
Why typically, okay.
Yeah, so.
In some systems you typically would split the anti-rollback.
Yeah, so remember, this is a roll forward, so I can come out with a firmware manifest, and in that manifest I can include a firmware version from 2 years ago, and inside the manifest it makes no difference. Yes, as long as the PFM rolls forward. So what that means is if I signed a PFM that had a firmware version in it that I said I should have never signed that PFM, I just flash it with another PFM, and I put the right firm pieces in there. So that's how we get to secure boot. So we talked a little bit about the attestation interfaces into this device. There is one through the host, which is the SPI interface, and then the out-of-band one is, of course, our I2C interface that gets proxied through the BMC. So incidentally, if we're sending something to Cerberus, we still have it encrypted with the certificate of the public certificate from Cerberus. So the BMC, although he's a man in the middle there and he's proxying the stuff through, He's got no way to decrypt what we're sending it.
Question about the golden image for the BMC. How is that vision? Is that a manufacturing time? Is it the first time you write a BMC in this flash?
It's the first time we provision Cerberus in that system is when we put in we put that into Cerberus firmware.
In addition to the AV images you already have?
Yes, yes. And it's kind of just a thing we stuck in there. It's kind of belt and suspenders, really, that we put in there for the event that somehow we had a bug in BMC firmware, and then we also had a bug in BMC firmware we couldn't get to Cerberus for some reason. Let's say we had a NIC bug in the BMC and it got all chewed up. We want to be able to use that as well to get back to a good state on the BMC.
So that also lives on the SPI?
That little image doesn't live on a SPI, so the U-boot image is tiny. So it's like a couple hundred K. So we stick it in the Cerberus flash.
So is it a BMC boot image or a Cerberus boot?
It's a U-boot BMC image. So it's a BMC bootloader image. So the BMC flash layout is U-boot, and it's usually like 200-300K, this thing. Then it's got a kernel, and that can be, maybe the 4 meg size compressed, and then it's got a huge root FS of like 12 meg, or I think OpenBMC right now is like 30 meg. The only thing we actually store a backup of is this guy. And but that U-boot is a pretty powerful bootloader that essentially lets you TFTP boot, or think of it like Pixie boot the VMC from another location.
Can you update that piece or no?
Yeah, we can update that. It has to be signed. We send it down as a signed update. It's not, it wasn't a part that we said, hey, we're going to include, but it's kind of this belt and suspenders thing that we just.
Flash up the ASIC as well.
We had the capacity of the ASIC, so we said we'll keep it in there, and we've never had to use it, so it's all good. So we've got more questions, Bill.
Hey, Nate, I think we're out of time,
Oh.
but I just want to apologize to everybody for the size of the room. OCP booked every room we could on this floor, and we ended up with a lot of different presentations, so we'll try to do a better job.
Hey,
I think it's a natural issue that we have with the growing community. Thank you.
Thanks a lot, folks. Sorry we ran out of time. Good question.